So thanks everyone for connecting. I don't know if you managed to look at the reminder email, but it contained a link to the repository that we'll be going through, as well as a blog post that also breaks down how you can implement a cost function approximation using FICO Xpress in Python. So that's today's topic. What we'll start off with is kind of set the scene in terms of how this approach is different from classical optimization and different from the usual machine learning setup. We'll do a compare and contrast of both, and we'll see how CFAs are kind of an adaptation of both of them being mixed together. So we'll go a little bit through that. We'll talk a bit about the complexities in practice that have brought about CFA. One of the things that you'll notice and that I'll bring up as well is that CFA is something that happens already offline without a data scientist or a optimization scientist being involved. It's actually done by the operators already by adding in buffers or any data modification to account for things that they believe will be happening based on their current experience. The next thing we'll talk about is reframing, how all of this leads to this reframing of optimization in practice and how cost function approximations do that. And then finally, we'll get into the soccer camp location example, which is a toy problem. It contains very simple elements to cost function approximation. We'll look at the implementation in Python. We'll look at an application, a web application built on top of that. And we'll also discuss a bit about how this could be extended to have more realistic either features or realistic settings, okay? So with that said, let's get into it. So I want to start with a full disclosure. So the motivation behind this, this webinar and all this work was purely curiosity. I personally learned by building, and I'm a huge advocate of sharing knowledge. And so this is me sharing my curiosity. I have not implemented this in practice myself in any of my actual work or jobs. I do believe there is potential in this approach, as I said, because this is an approach that is already somewhat done, but it's done from the operational side rather than from an analytic and scientific side. So this is more of a moving that mechanism from the operator to scientist. The real expert in this topic is Professor Warren Powell. He is the person who redacted this policy along with 3 other policies that encompass the entire universe of sequential decision making. Finally, this is, as I mentioned, this is exploratory work. I have not actually done this in practice, implemented it in practice, but I am interested to hear if anyone has done it and if they are able to measure the different outcomes that you get by implementing this approach. We'll look at how different or what the value is that you get from this by implementing it in this toy problem, but I'd be curious to see how this works in actual practice. So for me, what does success look like? Spreading my curiosity to the audience. I know this is a topic that has been trending a lot on the social platforms, professional platforms. I like to learn by doing, so that's why I believe while a lot of content contains information, there's nothing like actually getting your hands dirty with software. So that's why I wanted to do this. I want to provide tools for people to reference as well. So that's why the repository is open source. You can make contributions. And the blog post is publicly available. No need to sign up or provide your email or anything. You can just read it directly. And my stretch goal is that at some point, this actually becomes something that you all contribute to, that you all provide us information on how it's going when it's implemented out in your industries, at your companies, so that we can keep track of it. I think a lot of theory ends up just being theory and being written in books, but it would be great for us to kind of build a community around this and be able to follow up on it. So, is this not changing? So the full details of all that I'm going to go through are available in these two books, Reinforcement Learning and Stochastic Optimization by Professor Warren Powell and Sequential Decision Analytics and Modeling. So the one on the left is what he calls the big book because it is a very big book. It is over 250 pages. And the one on the right is the little book. So this is more tailored to undergrads. It contains some examples in Python and also is more focused on use cases and practical applications, whereas on the left, it is a lot more theoretical. Okay, so classic optimization versus classic machine learning. So the point from which I'm departing is that there is already a well-defined problem that has been aligned with stakeholders. So we already know it's a problem. We already know how to measure the outcome. What does success look like? And all this problem framing has already been done and analytics framing has been done. And we have decided that either it's going to be optimization or machine learning in these cases. So the usual flow in classic optimization is that once you have all the information about the problem, you have the input data. The idea is you build a model. That model consists of variables, constraints, and an objective function. And then you pass that model to a solver. It can be a heuristic solver. It can be an exact solver like FICO Xpress, and you solve it to global optimality. Now, in the case of using a solver, an exact solver like FICO Xpress, usually once we are able to solve to global optimality, meaning to an optimality gap of 0%, we often say this problem is done. This is as good as we can get. And then we operationalize the result from that solve. So we write it into our ERPs, MRPs, or whatever system of record that we're using, so that decision can be actually executed in the physical world. So far from the building and the solving, it's all a digital world. Even the writing into the system of record is still digital, but in the end, the idea is that is eventually translated into the physical world and operationalized. So in this workflow, there's a clear stopping criteria in model development, which is once you've built a model that can solve to optimality within the SLA or the time that you are allotted to do it, you have succeeded. There's nothing else to be revisited. You simply begin operationalizing and writing it out. There really isn't that much empirical testing. It's a practice that is taking on, it's being done more now with decision ops. I believe you all know the company NextMove. They are a huge advocate of decision ops. They're pioneering this field. And now this is being done more where they have, shadow testing or champion challenger testing, etc. FICO also has its tools to do something similar, where you essentially want to do some backtesting and see what the decision outcomes are in terms of one policy versus another, or one change in the model versus another. But more often than not, the revisit is really only triggered by some external event happening that causes the business to say, you need to change this in your model, or something wrong is really seen or something flagrant is detected in the decisions it's making, and then that goes to the data scientist or the OR scientist, and then the model is revisited and changes to the business logic are done, or improvements in the solve time are aimed for. So that's the usual flow. There's a clear stopping criteria, very little empirical testing. Machine learning, on the other hand, there is a consistent cycle. So usually you have data, you split your data between train and test, then you fit your model to the training data, then you test it on the testing data, and then you measure error. Error is always going to be there. It is something that you are assuming will consistently exist. There is no clear criteria as to what is the target error or any other prediction metric. And so it's consistent. It's a consistent cycle. You live and breathe, and you assume there is going to be error. Because of that, in practice, when these machine learning models are deployed, there is a general practice of having model drift monitoring. And so what that does is that the predictions that are vended every day or every time it's called, they are tracked versus some reality. They're tracked versus in terms of performance. And a lot of times, depending on whether the mechanism for monitoring detects that there is some sort of model drift, then it triggers either a retraining or a revisiting of the machine learning model. But essentially, that mechanism to detect is already implemented inside that framework. So there is a school of thought where we need to constantly and continuously be able to detect if something needs to change and automatically make those changes. Okay. So those are two philosophies, two very different ways of working. They're actually two different components in the analytics workspace. But here's how all of this comes together in cost function approximation. So in optimization in particular, there are many complexities. The two main ones are uncertainty and time. In terms of uncertainty, the literature has multiple approaches to it. So there's, for example, stochastic optimization, or what we call classic stochastic optimization, which is two-stage stochastic programming, multi-stage stochastic programming. There are packages available for that, for example, stochastic programs.julia. There's also robust optimization. So, for example, the well-known paper is The Price of Uncertainty by Bertsimas and Sim. There's also distributionally robust and two-stage robust optimization. For that, there is, of course, software called RSUM and Mazel, which is algebraic modeling language developed here by FICO. Mazel has a library for robust optimization called robust. And so it becomes very easy to translate your optimization problem, deterministic optimization problem, to a robust optimization problem by modeling or explicitly including things called uncertain sets. And then there's also stochastic dynamic programming. A good reference for this is a book called Foundations of Stochastic Inventory Theory. This is kind of the classic for it. There is a package that is being developed because dynamic programming often requires tailored algorithms. So it's not like, for example, optimization where you have general purpose solvers, but there is an initiative along those lines called DIDP. You can look it up. This is in the making. And then there's also learning simulation-based optimization, which this is somewhat a flavor of that as well. Now, in terms of time, meaning planning decisions that affect more than one time slot, the usual approach are time index models, and that can be either discrete time or continuous time. So there's a really good paper called Continuous Network Design, which is really good by Mike Hewitt and his co-authors. So that is another approach for it. And there's also, of course, the classic dynamic programming. So cost function approximations is going to try to address those two complexities while at the same time kind of merging two schools of thought in terms of dealing with errors and understanding that your optimization model is not fully going to capture everything, and so you consistently need to measure it for drift and errors. There are three main components in cost function approximation. The first is a parametric optimization model. So think of a usual optimization model that you get. You're going to get input data that you're going to use as part of to build your optimization model. There is going to be additionally a parameter that you can control that will modify some of that input data. And then, so you can think of it as you have input data coming from the system, you have a parameter that's going to adjust some of that input data, and then you build your optimization model. So that's kind of the parametric optimization model form. What is obviously different from the usual approach is the parametric part. There's also a simulator. So what you will do in your simulator is you will try to capture phenomena that are difficult to model. Sometimes there are certain phenomena that are difficult to model in optimization. It could be time-related dependencies, or it could be very stateful calculations. And you sometimes would need a simulator or huge physics equations. Sometimes you could use a simulator to simulate that part that is not explicitly captured in the optimization problem. So what we will be using the simulator for as well in this case is to capture the uncertainty and to kind of see how our policy will perform with given uncertainty. And then the final component is, as I mentioned, we have a parametric optimization problem whose parameter we control, values of the parameter we control. Then the question becomes, how do I update this parameter? And so there is the third component is the actual parameter update policy, so that you can decide how is it that after you simulate and then you see how your policy performs, how will that performance impact the way that I change the parameter for the next execution in the next time period? Again, this is sequential decision. These are sequential decision problems. So you're making a decision, this more or less the same decision, multiple times over a longer period of time. Okay. Some key observations here is this is exactly how, as I mentioned, this is how operation works. More often than not, sometimes operators will look at the input data and make manual adjustments. Most systems allow for this. The reason for it is they have outside information or they have beliefs that they want to see reflected in the data. And so sometimes they would add buffers just because they know machine A sometimes fails, or they know that a particular weekend there is an event coming up, or they found out that there was a viral event on social media, and so they will manually update the demand forecast. So these things already somewhat happen. Something else that is interesting, I don't think it's talked about enough, is that CFAs are stateful. Why are they stateful? Through the parameters. So the learned parameters, you're accumulating information on the fly that you are not capturing in your either your predictions or in your optimization model. And so there is a state of your optimization model at a given point in time. You're solving more or less the same model with the same parameters, but the value of the parameters are capturing some state in which the system is in, or the environment is in. And then the final point I want to bring up is that this forces strong empirical testing and monitoring. So here you are already assuming that the model is consistently changing based on the state. And so it makes it imperative for you to actually measure how the decisions are performing to see whether that state is reflecting properly or capturing properly the environment that it's supposed to capture. So what does this entire, so the question is, how do I build now this a cost function approximation given the tools that I have, okay? So I come from an optimization background, and so I'll kind of speak to it from an optimization perspective. So first, we start with the model here. I don't know if you can see my cursor, but I'm pointing at it here. You build a model just as you usually do, variables, constraints, and an objective function. And here there is a design choice as to decide where are you going to put the parameter in your model. Should it affect capacity? Should it affect demand? Should it affect allocation variables? That decision itself is an empirical decision. And so because there's no kind of, this is the right way to do it, this also promotes empirical testing to test what different ways of inserting the parameter actually work, or are actually capturing, able to capture and leverage the stateful, the state of the CFA. And then there's a training step in which, again, now you have your model, your parametrized model. You by solving the optimization model with whatever values of the parameters you have, you can always initialize them all to 0. So you would solve kind of just a naive optimization problem with no parameter values. And then you simulate. So you solve, you get a set of decisions, and then you simulate how those decisions would perform in the environment this would execute in. Based on the results of the simulation, then you decide, how do I update the parameters of the optimization model? So let's say, for example, you notice that you are consistently not meeting demand at a particular location, then you can make updates so that you add more stock to that particular location. And so you add a parameter that forces the optimization model to put more inventory in those locations where you're consistently out of stock. So you update the parameter. That parameter is then, updated in the model. You solve the model again, and then you simulate again. So you can do this cycle multiple times to learn, to kind of get the right state in the parameter. And then once you're satisfied with the training, then you can evaluate. So this is kind of a split between the training and the testing. So then you can test on another simulator, or you can test out in the field. And in the field, you can also do parameter updates as well. And you can also, it also helps for you to see how your policy performs outside of the training, the simulation training that you gave it. And once you're satisfied with that, you can, or if there is an issue that is triggered, you can then revisit the model. So if let's say you do one execution, you define a set of parameters as a particular place, you run the training, then you evaluate out of sample, and then you see that it's not performing well, you revisit the model, and then you decide maybe to put the parameter somewhere else. This is just the part to build the policy itself. And then you have the actual execution outside into the environment. You deploy it, you monitor it, and if you notice there is some degradation in the performance, then you can revisit this entire step again. Okay, so that in a nutshell is cost function approximations. So what we'll do now is we'll get into the particular toy example that we were discussing, that we'll be implementing. So the problem here is a soccer camp location problem. It's a take on the facility location problem. The idea here is that you need to locate soccer camps at potential parks to be used by interested students in those neighborhoods. You can, because the soccer camps are mobile, you can install a soccer camp at any park on any day. So you can decide to put one in the park near you, and then another one on the day after you do it in another park, somewhat more far away. As I mentioned, each day you can decide which parks to install soccer camps. No registration is required beforehand. You will get the registration on the very day. And so what that causes is that the demand is very dependent on the weather. So if it's raining, no one's going to want to come. Or if school was out late, then you'll see that being affected. You have demand estimates based on historical information. And your goal is to minimize setup costs and the overall transportation costs to soccer camps, from taking the children to the soccer camps. And you also want to minimize excluded participants. So you want that every child that wants to be a part of the soccer camp can actually participate. Okay. And you want to do that over the entire season, the entire summer. So that's the other component. The overall time horizon is an entire summer. The decisions that you need to make is on each day, where do I locate soccer camps, and how can you allocate the school demand to each of the soccer camps? Okay, so that's the quick overview, all the talking for now. Now let's get hands-on. Okay, so this is the application that we've built. This is built on top of Xpress Insight, which is a deployment platform. As you can see, I have multiple tiles here. Each one of these tiles represents an application. And I'll just go into the soccer camp location tile. And so this is our solution approach. So here, this is the problem that we had stated. As I mentioned, our solution approach is we're going to implement a cost function approximation. And we start with a parametrized optimization model, which is going to be essentially just a regular facility location. Anyone who's taken an OR course will recognize this. So we're trying to minimize fixed costs plus allocation costs or travel costs. We want to ensure that we serve all demand. So for each school, we want to ensure that proportionally 100% of the students from each school are assigned. And we also want to respect the capacities of each one of the sites or the schools. Okay. So this is a typical setup. What I want to call your attention to is where the parameter that we can influence resides. So here, the theta j is the parametrization that we're implementing in this optimization, this classical facility location model. We're adding this theta j, and that is the parameter that we are going to be using to capture the dynamics of the system that we are not explicitly modeling in the optimization model. If you see, we're not particularly we're not modeling here any missed demand or anything like that. It's just purely a facility location model. The other component, or the third component, is how do we update theta given realization of the simulation, and how do we update theta for the next time period. And so theta in this case is going to be updated as the minimum between 0 and alpha, which is a learning rate or a step size, however you want to call it. For those that know subgradient optimization, this will sound familiar. And then the delta, TJ, is defined as the excess demand unable to be fulfilled by the soccer camp's capacity. Said another way, delta is going to represent children who are excluded or were not able to be part of the soccer camp location. Okay. Now let's look at the data. So the way Xpress Insight works, it has scenario management built in. So this is called a shelf. I just clicked on it to upload the scenario. And here a user can look at the data themselves and modify them if they want to. So in this particular case, we have 5 schools. One thing this exercise tries to capture is also there, even if you predict there and you have a distributional prediction, there can be errors still between what the actual distribution is. And so if you see, we have 2 values for means. So we have the demand mean estimate, which is essentially a data science team and OR science team built this estimate based on data. And then we have the actuals. So this is what we're going to use when it's actually simulating. So this disconnect is trying to represent, for example, that even the best data science teams won't be able to make the right estimates of the distributions. There will still be deviations. And so this represents that difference. So we're really trying to model that possibility of having that disconnect. And the same for variance. So the variance that we estimate is actually different than the variance that the system will actually see. And this can happen because of multiple reasons. It can happen because of data limitations. Maybe they only took the last year and we should have taken 3 years. Or maybe this year is actually different. So, history won't necessarily repeat itself. But it's just something there to keep in mind. And the value of CFAs is actually that because the parameter is learning on the fly based on the simulation, it is going to more adequately be able to capture what's actually happening versus the uncertainty that you had modeled initially. For each site, there are 2 parameters. One is the site capacity. So let's say, for example, a park can only accommodate certain amount of only has a certain amount of space, so they can't accommodate more children. So you have site capacity, 78, etc. So this is the maximum number of students that can come here. And then you have installation costs. So right now we make it homogeneous, so everything costs the same to install. And this is just a map that I loaded. So the S's are essentially where the schools are, and the C's are the potential camps. So where we could set up camps. So there are, as I said, 5 schools and 11 camps. Okay. As I mentioned before, CFA works with a combination of simulation, parametric optimization, and in the update of the parameter, there is a step size, or you can call it a learning rate. Learning rate is here. You can define it here, so a user can decide to have a learning rate of 1. And for now, I'm going to simulate 50 days. I'm going to run this as if I'm making the decision for 50 consecutive days. Okay. So with all that information, I'm just going to run the simulation. And in the background, what this is doing is it's doing precisely as I mentioned. It first solved an optimization problem. And then once it solved the optimization problem, it's going to, in this particular case, it's only sampling one event, just sampling once from the distributions that we had previously seen. So we're assuming these are normal distributions capped at 0, obviously, because you can't have 0 negative children. And so we have, for example, we simulate that for school 0, the total demand was 32 plus 10, which is 42, which lies slightly above the estimated mean, but lies within the distribution of the actual simulation, because the actual system is 32 mean, but it has a high variance, so it still falls within that. In the simulations, we're actually using this rather than this. Oops, sorry. Here. Once we've simulated, then we calculate the deltas, which are the children that were unable to get to a soccer camp, so the excluded children. And then we update our penalties, or the theta. So in this case, before the simulation and adjustments, the original values of theta were just all zeros. We initialized with all zeros. However, after the penalties, after the simulation and then adjusting for the unmet demand, we see that campsite 5, we put it to -12. So what we're saying is, in the next iteration, you are going to think that you have less capacity than you actually do. Okay? So that's the logic behind this. And so what it's going to do is, if it's opening 5, it's going to open 5 and something else to meet the demand nearby. That's the idea behind it. And then we do it again in the second iteration for the second day. So now we've optimized now with this set of parameter values, and we optimize, we get a solution, we simulate again, we sample again, and then we make other updates again. So here in the first, before optimizing and modifying the parameters theta, these are the values we had, same as the ones before. But now we see again that we still had unmet demand, so we adjust again site 5, and now we also adjust site 6. And we do this consistently for 50 days. And the result of that is, so this is produced at the end. This is very easy to configure. You can do this by drag and drop and configure what type of tables you'll show, what type of graphs you'll show. So I can show this later, but essentially this can be done very quickly with Xpress Insight. As you can see, what this represents the pie chart of the frequency of the solutions. So opening site 5, site 6, and site 10 appeared 32 times out of the 50 days that we ran. It had a total cost of $1,800. That includes only cost of installation and transportation, but it had an average excluded participants of 0.2 over the periods that it appeared. There is also C3, C5, and C6, which has a lower cost, but it has a slightly higher number of excluded participants. And then finally, we have C1, C5, and C10, which appeared only 6 times, which has a similar cost to C5, C6, and C10, but the average participants, excluded participants, are higher. Here we can track, for example, the performance of each one of the costs based on the iteration in the simulation, so day 0 all the way up to day 50. You see it here, the average costs. And here what I've included is the actual results day by day. So iteration 0, 1, 2, 3, all the way to 50. As you can see, even if you have the same open trucks, because there's a simulation component to it, there are different values of the excluded participants, because that's the part we're trying to capture from the system through the parameters. So here, for example, you have, even though it's C3, C5, C6, you have 13 excluded participants in this instance. But in others, some of them you have 0, some of them you have 4. This number that we look at here is purely an average of all of these. Okay. Again, when you think about an optimization model, oftentimes we only look at one day and that's it. In terms of CFA and you're looking at sequential decisions, you want to think about it over periods of time. And so that's why the metrics that we're looking at here are averages. And so let's say we want to try out, and this is where the experimentation comes in and where Xpress Insight is very, very useful, is let's say you want to try a different learning rate. So let's say learning rate 0.75 or 0.7 instead. So I've created another scenario. I can click on it here. I can move it here. So by moving it to the left, that means that that's the scenario that I am going to be modifying. And so what I'm going to do is I'm going to modify the learning rate to from 1 to 0.7. So I'll do that there. And then now I can execute. I'm going to run the simulation. I'm going to keep this one here because that allows me to do a comparison. And I'll show you how in a minute. So in this case, I'm a learning rate of 0.7. So I'm learning less per se. And because I'm learning less, I'm actually getting the C3, C5, and C6 solution many more times. So if you see, I got predominantly this solution 94% of the time. It has a 1,700 cost, average cost, and the average excluded participants is 1.4. Okay. Again, similar details I can see here as I start. But as you can see, as I simulate, I'm getting more zeros because this is appearing more times. But sometimes it does change, but it doesn't change enough. You see, for example, here, I had 2 excluded. It wasn't enough to actually change it, so I kept it. However, on day 46, I had 14 exclusions. And so immediately after, I updated the policy, the parameter, sorry, and then I got a different solution. Okay. So that's kind of what you can see in this pattern of learning. With Xpress Insight, something else that we're able to see is we can compare these 2 scenarios side by side. So here, for example, I have I'm ranking, I'm matching based on the rank. So with a learning rate of 0.7, 3, 5, 6 is the predominant solution, whereas 5, 6, 10 is the predominant solution for with a learning rate of 1. And here I can see that, for example, if I'm trying to look at the excluded participants, 3, 5, 6 has slightly higher excluded participants versus 5, 6, 10. So I found 5, 6, 10 first as the predominant solution here. Whereas on the other hand, if I look at the second most frequent solution, in each one of these, I have 5, 6, 10 appearing as the second most frequent solution. And the average excluded participants here is actually 0. So here I can see that this solution, on average, when it does appear, it does have a lower value of excluded participants versus 3, 5, 6. And that is consistent in both a learning rate of 0.7 and 1. So the learning rate really influences what solution appears the most frequent. In general, the learning rate also helps you adjust to the dynamics of the situation, of the environment. And so that's kind of the comparison that we see here. So we get 2 of the same solutions. We get the 3 same solutions. They just appear less frequently or more frequently based on the learning rate repeating solutions or changing solutions. Here we have another bunch of graphs that we can do. Here's the progress that we made in terms of costs. So as you can see, they all start at the same point, but at some point the learning rate of 1 is higher versus the learning rate of 0.7. And this is kind of, you can see the excluded participants. There aren't directly correlations between the two, as you can see. They have spikes at different points in time, and that is in general because they have different solutions at different points in time that are simulated. Okay. One nifty thing I wanted to show is, so this is Xpress Workbench. This is essentially what I use to build these visuals. It's an IDE. It includes your entire project. So all the code is available here. This is the code that is already available in the repo. So you have access to all of this. And you will have these .vdl files. If you open this on Insight and you look at the VDLs, let's say I want to change this because this is now bothering me. I should have detected this earlier. Rather than calling it a step size, I'd like to call it learning rate, which is more consistent. So I can update the learning rate here. And what I do is I simply publish this change, and then I can see this reflected in the application, in the web application. So see, it's upgrading. So here I have updated learning rate. So I can test different learning rates. I can test 0.9 or whatever. So this is kind of the setup. This is how you would operate with CFA. Now let's look at the coding part, which is the part that we all want. So the coding itself, this is the structure of the repo inside that I shared with you previously. The application that you saw just now is all that code is located here in Soccer Camp location app. And this is the general structure of an Insight application. However, in all the Python code that builds all of this is in the Python source. So I have a habit of decomposing my code into different parts, so kind of have as much separation of concerns as possible. But the part that is interesting for us in particular are the functions located in simulator.py. As I mentioned, there are 3 components, main components in CFA. First, one is simulating demand. So here what we have is the function that simulates demand. It receives an instance. An instance is just a whole, it's how I encapsulate all the information, all the input data. It receives the information of the decision, so which soccer camps were built, the solution, and whether I'm training or not. So this is, we can get into details. You can get into details of that offline. It's not really relevant in this point in time, but essentially, if this is on, then I'm sampling from the estimates, from the demand estimates. If this is off, meaning I'm not training, then I'm simulating off the actuals. So that's just for me to be able to capture the disconnect between what I estimated and what is actually the system, how the system is actually occurring. Here I'm just pulling the stats based on whether it's the estimate or the actuals of it. And here, this is just me simply sampling a demand realization. We can make this part as complicated as we want. We can do multiple sample paths and take average performance. Right now, I'm just taking one sample, and then I'm calculating its performance based on that. So what I do is once I sample the demand, then I look at capacities. Capacities is essentially my delta. So the delta that I showed you is capacities, which tells me did I have any unmet demand from it. And then what I do is I vend out that vector of unmet demand. So this is the simulation part. Essentially, I'm taking in a solution. I take in whether I'm going to simulate based on training estimates or the actual system estimates. And based on that, I subtract whether I was able to meet all the demand or not. And then I vend that information. Okay. adjust opti penalties is the parameter update. And so as you can see, I have here capacities, which is going to be my delta. I have penalties, which are going to be my theta, and I have the step size or the learning rate. So maybe I should have kept step size before, but anyway, the step size or the learning rate. And so what I do is penalties is capturing the states. The thetas are capturing the states, and so that's something that I will be persisting and keeping throughout the process. Whereas capacities is ephemeral; it is only for that particular time. And so here, what I do is I simply update the theta based on the missing demand, and then overwrite the values of the penalties of theta. And then finally, or the principal component, the one that I like the most because this is optimization part, is the optimization problem. So here I'm defining the optimization problem. This is a typical facility location problem. I'm adding the objective function constraints. I receive as an input, of course, the penalties, and the penalties are reflected here, as I mentioned before, in the capacity constraints. So I say whatever the capacities of the trucks are, minus the penalties, multiplied by whether I build it or not. So that's the available capacity. So I'm modifying the available capacity in the optimization problem based on the penalties. Okay. So that's the main part of this. This code is all, as I mentioned, available to you, and it already runs right out of the box. So you should be fine. All the other pieces of code, they're not necessary. They're more just for the way I code. Application.py is how I configure the application that I showed you, the web app. So all I need to do is add this and declare kind of the data schema, what pieces of data I want the user to be able to interact with, what are the names I want to display. And then there's a load function, which will load the data from the environment, from some input files that I've given it. And then the run, which can be just run an optimization model, or in this case, you can run an entire simulation, optimization, and parameter updates. You run an entire CFA process over time here. This is what we do in our run. And then the other files are just, instance is just encapsulating all the information in one. Main is just the main execution flow, and these are just plotting functions, and of course, a setup.py just for packaging purposes. Now let's execute this all together to see how it all comes together. So here we've already went through it, the methodology, the formulation, and here is the code. So I'm going to start by just initializing everything. I'm going to fix a random C just because I want this to replicate and get consistent results. I'm defining where my data files are. So it's inside soccer camp location app in the attachments. Here are the input files. That's what it's reading. So I'm reading this manually here in this Jupyter notebook. So this is outside of the application. This is just so that we can go through it through a notebook and see and play around with the results as much as we want. I instantiate the instance. So here I give it the set of schools, set of sites, and the distances that it's going to read from. And I'm just defining paths to write out the solutions and the images. So this is the main execution flow. So this is what we're running in the background in the main file. As I mentioned, we're starting off with the penalties. Here I'm accumulating all the penalties. So as I mentioned, you can play around with the penalties or the thetas as much as you want. You can use just the last theta that was calculated, or you can use kind of like do some exponential smoothing across the thetas. There's really a lot of possibilities here, and this is similar to like an ML setup where there are multiple things that you can play around with and empirically test. So that's kind of the reason why I save all the penalties. And here's the simulation part. So as I mentioned, what I'm doing is I first optimize with an initial set of penalties, which are all received and they're initialized at 0. once what I get from optimize is a set of a solution. So what did I build and who did I serve and what does the graph look like? And so I also, if we're able to get a feasible solution, then we print it out. If not, then we just say it's infeasible and we stop the loop. So once we have the solution, we simulate demand. And then as I showed you before, we simulate demand and then we get capacities. So here are the capacities. So essentially the unmet demand. And then based on the unmet demand, we adjust the penalties. And then we add the new penalties to the list of all penalties here. And then this is just purely printing. We record this information so that we can consult it in a table afterwards. And that's it. And that in a nutshell is all the code you need to build a cost function approximation. So let's make this work. Let's do a few steps of this. I don't know if this worked. Yes. So in this case, in this part, I'm training. I initialize all my thetas to 0 in this case. I'm going to simulate 20 days, and it's going to be, I'm going to give a step size or a learning rate of 1. And so I'm going to call CFA, which is the function I just reviewed above here. And I'm going to give it the number of simulation days, step size, and the penalties. So I'm going to run this. So it's simulating 20 days. Again, this is similar to the output you saw in the application because this is the same thing that's running. It's updating the theta before and after the adjustments, and it's doing that for 20 days. So I've trained it. I have some information. I have a set of all the thetas, and now I'm going to test it. So here I'm going to do out of sample. So if you see here, the train flag is set to false. So I won't be sampling from the estimates that I used to train, but I'm actually going to sample on outside performance. So outside distribution, not a sample distribution. And so I can run this. It's going to do the same thing. I'm doing it for 50 days. It's a long output, just 50 days. And what I'm doing here is I'm doing a baseline. So in this case, there is a step size of 0, meaning I'm not learning anything. And so essentially, this is kind of comparing what would happen if I just simply ran an optimization model as is with no parameters, updates. So essentially, it would be just you'd get the same result every time. And essentially, the model doesn't capture unmet demand, and it is fixed. But we'll measure what the unmet demand is. So this essentially is going to show you what the cost of doing things the old way would look like. So it's doing that. And now we'll compare the two metrics. Okay. So if you see, the baseline optimization, of course, has a lower objective value because we're not capturing unmet demand in the objective function. It's just kind of, it's just purely cost. So installation cost and allocation cost. Obviously, this is going to be lower. Total serving costs and total truck installation costs are lower as well. Well, installation costs are the same, actually. But if you look at the missed demand, you have on average 53 missed demand. So this is over the 50 days, you had 53 unmet demand, or children who didn't get to play soccer. Whereas with CFA, you have more or less the same model. It's just the parameter that you added. It's slightly more expensive, but you've been able to cut that factor of missed demand by half almost, or more than half, actually. And so that's the value of it. You've kept the same model, you same everything. You're not changing. You're not making your model more complex. You're just simply adding a parameter in the right place where you can recalculate and influence the optimization model to learn from the actual system. And then we can also test with a different policy. Now we're testing with a step size of 0.5. So we can run that. And the results look more like this. So in this case, it's true I get a higher cost overall in terms of the objective value of total cost, but I can reduce it further. So here in the total, I reduced it from 25 to 11. So I reduced it even by half. And so because of this dynamic, you're forced to look at, test empirically, talk to stakeholders, see what makes sense. Are you willing to pay that extra 1,500, etc.? But it changes the mindset to be more like dynamic. And you have this stateful artifact that is going to learn from the actual system. So it doesn't matter if you didn't model uncertainty great, it's actually going to learn on the fly from the actual system. So with 2 minutes left, sorry I took the whole hour, but I'll leave it there and I'll take any questions.